Okay, next we have question 15. Weightless. Okay. So right now, if you're standing on the earth, do you feel weightless? Think about what if you jump from like a table. Before you reach the ground, will you feel your own weight when you are jumping?
No.
You won't, right? So what actually makes you feel your own weight?
Reaction force.
The reaction force, the force that's supporting you, right? Think about it. If you're in an elevator, we feel our own weight. But what if something wrong with the elevator, somebody cut the cable, and then the elevator starts to free fall, and you are together free falling with the elevator, will you feel your own weight? No. Why? Because there's no reaction force provided by the elevator, right? So, in fact, the reason why you feel your own weight is because something else is supporting you from free falling. That is the reaction force provided by the ground or anything that you stand up on, right? To stop you from falling, that's the only way you feel your own weight. If you don't feel your weight, that's because there's nothing supporting you. You are free falling, then you don't feel your weight. You're falling together with everything else around you. There's no such thing can stop you from free falling, then you don't feel your own weight. So in this case, a spacecraft orbits the Earth, which is in outer space, and there's a space station. An astronaut inside the spacecraft feels weightless because, okay, is it because there's no gravitational field in spacecraft?
Yeah.
No, there is still gravitational field, right? Even if the spacecraft is orbiting around the Earth like that, if it stops moving, the gravity still can drag it back to the Earth. There is gravitational field. There is gravity. Okay, that's the first thing. Second thing, because the Earth exerts equal force on the spacecraft and the astronaut. Is that possible? The Earth exert the force. What's the force that the Earth exerts on everyday object? Their own gravity, right? So we know that gravity, if on the Earth's surface, is equal to mass times acceleration, right? If you are at the same spot, then the g, if you're same distance away from the Earth, the g is the same. Gravitational field strength is the same. Then it purely depends on your own math. Can you imagine the astronaut has the same mass with the spacecraft? That's an alien, right? I don't even know if alien is that massive. So, no. C. The spacecraft and the astronaut have the same acceleration towards the Earth. That means they are both free falling. But you might think, wait, how is that possible? They're not falling. How do we define free falling again? What's the process of free falling when we learn it in MIP grade 9?
Only gravity.
If the force acting on the object is only gravity, there's no other force, right? Isn't it the same for the spacecraft that orbits around the Earth? In the outer space, there's no air, so no air resistance. The only force acting on them is gravity. Except the gravity here is not dragging them down, but the gravity here is changing their direction. The gravity here, the acceleration here, does not change the magnitude of the velocity, but changes the direction of the velocity because the gravity here serves as a centripetal force. So we say that both the space and the astronaut have the same acceleration. If they have the same acceleration, which means the spacecraft does not provide supporting force to stop the astronaut from falling. Then, if both of you are free falling, there's no reaction force. If there's no reaction force, you can not feel weight. Yes, exactly. Okay, so that's number C. Number D. exert equal but opposite force on each other. That is how you feel let's say if you accidentally crash on the wall of the spacecraft, you feel the force, yes, but that's not your weight, right? That's not your weight. That's not the reason you feel weightless. So D is irrelevant. D is irrelevant. Okay, question 16. If,需要讲吗 question 16? Okay. A frictionless trolley of mass m moved down a slope with a constant acceleration a. A second similar frictionless trolley has mass of 2m. The acceleration of the second trolley as it moves down the slope is. Okay, so let's draw a slope. So the trolley frictionless has acceleration of a. Okay. Can we use Suva to solve it? Can we? I'm asking.
Yes.
Yes?
No.
Isn't it constant?
You don't have anything else, how do you do it?
SUVAT, what do you know?
Oh, I mean,
Other than A, what do you know?
no, I mean, we cancel if we have the value.
We don't.
For this question, you cannot use Suva because in order to use Suva, we have SUVAT. You need to know at least 3 to solve for the other 2. But in this case, we don't know S. Maybe it doesn't say if it's released from rest. It doesn't mention if it's released from rest. So this, we actually don't know. Final velocity, of course not. A, sure, but we don't know T. We don't know this. Basically, we only know A. So there's no way you can solve it using Suva. Which means we can only solve it by draw a free body diagram using forces analysis. We have to analyze the forces acting on it using Newton's second law because forces and acceleration are related. Now, what forces are acting on this trolley?
Wait.
First of all, gravity, weight. Second of all, normal force provided by the slope, which is going which direction? Perpendicular to the surface. Anything else? Friction?
No.
Frictionless trolley. So only those 2 forces. Isn't it something that we already done on Tuesday?
Yes.
So how should we do it? We need to decompose what?
Acceleration.
We need to decompose weight. So what we're going to do is we draw a coordinate that's parallel and perpendicular to the slope. If we decompose this weight, this here is what component? X or Y? X. This here is Y component. What's the relationship between those Y in the Y direction?
Same.
Same, because they're not moving in Y direction, right? So Y direction, they must cancel out. They must cancel out. So N equal to WY. Is there anything else in X direction other than WX?
No.
So WX, if those 2 forces cancel out, if those 2 forces cancel out, you decompose weight, so the only thing left is WX, right? WX is the net force, right? Which means WX is the net force F net, which should equal to mass times its acceleration, right? How do we calculate WX? WX is a component of weight, so let's start with the triangle here. Let me use the black one. We know W. This is WY. This is WX. So in this triangle, right triangle, here is WX, here is W. Let's say this angle is theta. Then WX is the hypotenuse, opposite or adjacent? Opposite divided by hypotenuse gives you sine theta, right? So WX over W is sine theta. Thus, WX equal to W sine theta. W is
And
mg. So this equal to mg
size.
sine theta, which equals to the net force MA. M cancel out. So acceleration is g sine theta. Acceleration in this case it only has a relationship with the angle theta here. It has nothing to do with the mass. So if you don't change the slope, if slope stays the same, no matter what mass you use, 2m, 3m, 10m, 100m, 1000m, it cancels out. It doesn't matter. The only thing matters here is the angle theta. Okay? So, how do we understand that? Let me give you a demo. Two-meter ball, definitely different mass, right? So if we roll them down on the slope, same angle slope, they should have the same acceleration, which means if I release them at the same time, they should reach the ground also at the same time. So let's do if it's the same. 我需要用个管子吧，用两根管子。哦，我是这个。
电的。
啊，对了。
拿个东西电的。
啊？
把它电的。
对，重点要对齐，而且它这个管子长度有点不一样。我先稍微过来。Okay, 1, 2, 3. Together, right? 还有一个球到哪里去了？喂，啊。So, but if I change the angle, let's say, 再帮我后缀一下，这个高一点，这个低一点，中间不用对齐，没事。你这边帮我后缀一下，两个。Okay, if this the case, 然后你这只手堵住，不要让他们跑。One, let's say which one is faster? Can you predict? Okay, 1, 2, 3. 啊，我放的时间不一样，让我重新来。Alicia， 你来帮我一下，来放这个，放下面。1，数到3放啊，1、2、3。来 ，OK。再来，我现在把小的放上面，看看 mass 到底有没有用。你不要完全堵住，完全堵住有 air resistance。1, 2, 3, go. Now, whoever is on the top will reach the with the greater angle will reach the ground first. Okay, so that's the demo. Thank you guys so much. So now, is it clear that it has nothing to do with the mass? It is only a function of angle. Okay? Alright. Question 17. So, right now here, I have a scale, just like this girl here, right? I press it. It's not 0, so I 去皮, now it's 0. Okay. But you see, when I move it, it has reading and it changes, but there's nothing on top of it. Air resistance, or let's say if we say it measures the weight of something, right now it's 0, right? Right now it's 0. If I put this, So the mass of it is 41.3 gram, right? But if there's an acceleration going upwards, or let's see, going forward, is this thing greater or smaller than? It changes, right? It changes. So, but, or even if like that, there's no way, just my finger pressing on it. It changes as well, right? So what exactly is this reading? Is this reading reflecting the weight, the weight of that object, or how hard you press on the scale?
How hard it
When stuff stands still on this, the level of difficulty, the how hard you press on the scale is, the magnitude is equal to your weight, right? But if, let's say, you're jumping, like right now, it's 41.3, right? Okay, read this thing when it just collided with it, right? 60 something is greater than 41, right? Okay, why? Because basically you have a downward thing that causes giving the scale an extra step. Okay, so basically the scale, the reading of the scale is the force that you acting on the scale. When you stand still, when you don't move, the reaction, the force that you press down on the scale equals to your weight in magnitude. But whenever there is an acceleration, this does not hold true, right? So, but anyway, here it already says that the reaction force from the scale is R, which means R provides a reaction force to you. That's the amount of force that you exert on the scale. Action is the force that you exerted on the scale, right? Reaction is the scale supports you. Those two forces, no matter what, is equal but opposite because of Newton's third law, right? And the reading of the scale is always how much force you press on the scale, which is equal to the reaction force of the provided by the scale to you. So just R. Questions? 讲题是讲了一节课呀，
好了，第18题看到了。
5分钟不休息了。Sorry. Question 18. A lamp of weight W is suspended by a wire fixed to the ceiling. With reference to Newton's third law of motion, again, Newton's third law. So step one, you need to identify two objects. The force is equal but opposite to W is. Now, what is this W? This W is acting on what? Lamp. So that's your object A. So this W is caused by what on a lamp? Earth. Object B is Earth. So this W is the force B give to A. So an equal but opposite reaction should be A back to B. So this force should act on Earth. So tension in the wire, no. Force applied by the ceiling, no. Okay, force exerted by the lamp on the Earth. That is correct. C. Get it? 好，作业讲完了，还是给你们2分钟休息吧。Okay, let's keep going. So did we finish about momentum yesterday? I think we were somewhere here, right? Talking about the FT graph. Remember this? So we were here, right? Okay. So y is the red positive
Direction.
direction, right? What does the area below the FT graph represent? Impulse. The impulse is a vector, changing momentum vector. Okay. So impulse can be positive or negative. It depends on the direction. Depends on the direction. All right, let's look at one example problem here. A 0.14 kg baseball comes in contact at 40 meters per second, strikes the bat, goes back out at 50 meters per second. If the collision lasts 1.2 milliseconds, find out the impulse imparted to the ball from the bat during the collision. How can we do it? 2 minutes, discuss with your classmates, and then I'm going to invite 2 students to share with us their thought. Discuss with each other if you don't know how to do it. Okay. 1.68. Anybody got the same answer? Yeah? Anybody else? Okay, let's check answers then together. So, that's how it works, right? You got a ball here, and then you use a bat to hit it. So it bounces back at a greater speed. Now, when they collide, the forces acting on each other, what are they? When they collide, the forces between each other are what pair? Action, reaction, action, and reaction. So this is the before stage, this is during stage, or after, okay? So, like I said, whenever you are dealing with collision, you always need to follow total momentum before, total momentum after. And momentum is always conserved during a collision or an explosion. So, total momentum before should equal to total momentum after. But in this case, what we know is the time taken. So how can we do it? Momentum before for this one is 40 times 0.14, which you get negative 5.6 kilogram meter per second. Impulse is basically change in momentum, right? Change in momentum. So after that, can you calculate the after momentum? Which you get positive 7. So changing momentum is impulse, which is P final minus P0. Since P0 is a negative term, so you positive 7 minus negative 5.6 is actually 7 plus 5.6, which you get 12.6. That is correct. Now, but remember Mr. Kai said momentum should be conserved. In this case, why is momentum not conserved? Or this change in momentum of 12.6, there should be a negative 12.6. Where is that negative 12.6? The back, very good. So, when this ball comes, firstly, it has this much negative 5.6 momentum. And then the bat apply force on it. So give it 12.6 of positive 12.6 of impulse, which changes momentum by this much. So 5.6 to cancel it, the rest 7 becomes its new momentum. Now, because the time that they're in contact is the same, and when they collide, it's action and reaction, so the size of the force is also the same. So changing momentum is the same for both of them. The bat changes the momentum of this ball by 12.6. Then in return, the ball also changes the bat impulse or momentum by negative 12.6. So that total momentum is still conserved. There is no change in total momentum if you take the bat and the ball as a system. Okay? Alright. So, the unit for changing momentum can also use kilogram meter per second. It is the same as Newton second. Okay, move on. Questions? Now, how about we find the average force? What can we do? After we know that 12.6 is the impulse. How can we find the average force? Darren. After we know that impulse or changing momentum, I or J equal to 12.6. How can we find the force? Average force.
Divided by changing time.
Divided by changing time, exactly. So final answer you get 10,500 Newton. Questions? Okay. What we calculated is just average force. But during impact, the force is actually changing. That would be more difficult and more complex, so we won't test you. We just need you to find out the average force. This height here is F max. What we're looking for is if we draw a same area, then this height is F average. Okay? Alright. Can I erase it? Okay, let's move on. See? This red jet F is the F average, is the F that we're calculating here. Okay, area under the graph, we pretty much know about it. We can skip it. Basically the same way in MYP when we find the area under a speed time graph represent distance traveled. This one is a interesting one. Let's look at the thrust. How does jet engine produce thrust? Well, basically, let me show you a little demo with the balloon. So I have a balloon here, right? I can blow it up. What if I let go? It flies, right? But why would it fly?
The air pushes up.
The air inside is being pushed outwards, right? So the air will be pushed downward. So the balloon pushes air downward. According to Newton's third law, in return, air should push the balloon upwards. Sorry. Okay. So here is the same thing. The engine sucks the air in and pushes the air backward, right? So according to Newton's third law, if the engine pushes the air backward, air in return will pushes the engine forward. That's how we make the jet fly forward. So now the jet engine sucks in air at about the speed that the plane is flying through the air, heat it up and expel it at a greater velocity. So we have initial velocity of u and greater velocity of final velocity greater of v. Now this momentum of air changes since its velocity also changes, and hence an impulse has been imparted to it by the engine. If the engine gives the air impulse, in return, air should also give the same amount of impulse back to the engine to change its momentum, right? Okay, so the engine thus feels an equal but opposite impulse. Wait, why do we, because we always say equal opposite force, but what is this impulse now? How do we calculate impulse again? Other than changing momentum, there's another way to calculate it. Force times time. And for action and reaction, they appear at the same time and disappear at the same time. So the time duration is the same, right? So action reaction, same. Time, same. So impulse is also the same. Equal and opposite. Good? Okay. And hence, the engine creates a thrust that pushes it forward. Okay, now let's look at this example. So show that F equal to delta. 需要做吗？看一下步骤就好了，好不好？ First of all, from F equal to delta P over T, changing momentum over time. That's the definition of force. So here in dP, if you are asked how do you define force, the definition of force is change the rate of change in momentum. Okay, similar to velocity and acceleration. How do we define velocity? The rate of change of displacement. How do we define acceleration? Rate of change of velocity. Here, how do we define force? Rate of change of momentum. So changing momentum can be expressed by delta brackets mv. Now, in dP, mass could change. Mass is not necessarily a constant anymore. Okay? In MYP, we keep it simple, we keep it low key. Mass is a constant. In dP, mass can change. That's what makes it more complicated. Okay? So if V is constant in this case, then we can get this equation here. Alright? So Alice, would you please read this for your information? Okay, now this equation says that V is a constant. Then the only thing that can change is the mass. Why is this true or applicable to a rocket, Jessica?
Because the fuel is burning.
The fuel is burning, you're losing fuels, right? So mass is changing, right? But we can manage to keep the velocity at a constant. Find a way to keep that. Okay, so this is applicable to the rocket engine. Questions? Okay. All right. Okay, let's move on. All right. What is the purpose of the rocket nozzle? Let's look at this. So, in a combustion chamber, the gas particles have random direction. But when we have the shape of the nozzle here is such that the particles in the sphere of the combustion are deflected in such a way that they all come out anti-parallel to the rocket. If they're coming out anti-parallel to the rocket, which means they're moving in the opposite direction that rockets move, right? We want that because that's actually how it pushes rocket forward. We're pushing the gas backward. Right? Okay, so this is the rocket nozzle. The shape of that is because we wanted to redirect the gas after combustion, because that's random, into a parallel opposite direction, so that it pushes the rocket upward. Okay? Questions? Right. Let's move on. So we've done this before, don't have to do it again. This we can take a quick look at it. So linear momentum, conservation of linear momentum is basically the conservation of momentum that we learned in NYP, because we didn't learn angular momentum. SL you don't need to worry. HR you need to learn angular momentum and conservation of angular momentum in A4. So net force equal to delta P over delta T. Okay, delta P over delta T. That's how we define forces. But what if the net force acting on an object is 0? Then we have net force equal to changing momentum divided by changing time, which is 0. Changing time cannot be 0, so changing momentum must be 0. And if the net force is 0, the momentum does not change. P is a constant. Which makes sense, because if net force is 0, then there is no acceleration. If there is no acceleration, velocity don't change. As long as it's not rocket, usually mass is a constant. If mass is constant, velocity don't change, then changing momentum is 0, because there's nothing changed here. Mass don't change, velocity don't change, momentum don't change. Questions? Okay. So, pretty simple and straightforward so far. Lucas, can you read this for information?
If during a process the physical quantity does not change, that quantity is said to be conserved.
That's what the word conserve means, okay? It just doesn't change its quantity. Okay. Alright, so changing momentum, again, we have done a lot of practice in MIT. Well, does anyone who didn't learn this before? momentum and collision 没学过是吧 Alright, 那我讲一下吧 slow it down. That's the reason why I need to ask you guys if I'm being too fast or too slow. You need to give me feedbacks so that I can adjust my teaching speed. Okay. Most of you I have taught you ever since you're grade 8. So if you're grade 8 or grade 9, you're with me, I know what you have learned. But if you join later, I don't know what you learned before. So if you didn't learn this, you need to let me know, right? Otherwise, I asked, nobody say anything, then I thought everybody's learned, so we don't need to waste time. But in this case, as long as we have someone didn't learn, we will have to talk about it. So, let's look at this conservation of linear momentum, right? Again, during a collision, right, two balls interact with each other. Let me drag two balls. How about golf balls? Anybody plays golf? Do we have a golfer here? Nobody plays golf?
我有一点。
哦，算呀算呀，打过就算呀。你也玩过吗？哦，professional。golf 有多少级啊？有什么动作机器吗？我只知道看起来很帅。头不能动。那我就摇个晃不是。Okay, all right. Golf aside, let's look at this example. So, how would I demonstrate it? First of all, actually, let's measure the mass. I wanted to make sure that those two golf have the same mass. This one has 44.5 grams. Okay, slight difference. We can ignore it. Alright, so if these two are the same mass, right? Then in idea, when they collide, their velocity can swap. So if one is stationary, the other one is not moving. If we collide them head on, that's an ideal situation that 很考验这个人的技巧，所以很有可能我没有办法 head on， 因为我的技巧很差。So let's see if I can move this to hit this one, and then this will stop here. This one will keep moving. 哎呀，不行。Well, the reason why both move is because they didn't collide head on. So if they collide like that, this will move this way, this will move that way. That makes sense? Okay, let's do it just one more time. 哎呀，不行，我的技巧太差了。哎 ，maybe use a 导轨。啊，但是这里有那个导轨。
管子有用吗？直接放管子里面然后推。放轨道上面的一推就好。
So, hopefully this will confine them in just one direction. And hopefully, when I collect, because they are the same mass, hopefully this one will stay, well, roughly the same mass, there's still mass difference. Hopefully, when this collide with this will move forward and this one will stop. Okay. Or
没有，你扒的时候，老师加了额外的 rotation 不会。老师在撞时加了 rotation。
啊？
啊？
什么 rotation？
你不能这样子。
这个很好，对吧？这个 demo 就很棒。Very good. So that's what it means, right? When they collide with each other, the reason why I use this ball is because we want to make sure that the only forces that interact with each other is their internal force. If we take those two balls as a system, the force interact with each other is internal force. The weight of themselves is balanced by the normal force, right? The friction, since they are rolling friction are super small compared to sliding friction, right? So it can be ignored. In this case, if we ignore the friction and air resistance, then there's no external force. Then internal force cancel each other, momentum is conserved. So 我先把这个撤掉，有点危险。Okay, so let's see. Now, Newton's third law guarantees that internal force is zero. Why? Because action-reaction. We take this as a system. They collide with each other. Action-reaction. So opposite and equal. Usually, action-reaction cannot cancel out each other because we're taking individuals. But now, if we're taking in as a system, two balls collide within a system, action-reaction can be cancelled out in a system, but not individual object. Does it make sense? Okay. Alright. So then we get if external force is zero, then momentum is conserved. Do you still remember the law of conservation of momentum that we learned in MIP? What does it state? Marvin.
Total momentum, initial total momentum should equals to final total momentum.
Momentum before collision should equal to momentum after collision. When there's a condition, when in a closed system there is no external force, right? That's the reason why. That's the reason why here. Because F net equal to external force plus internal force. Internal force can be cancelled out within the system due to action-reaction, equal but opposite. External, you have to make sure there's no external force, right? Such as friction or any other human factors. So let's look at this example, okay? 2,500 kilogram gondola car traveling at 3 meters per second has 1,500 kilograms of sand dropped into it as it travels by. Find the initial momentum of the system. That's easy. So what's the initial momentum? It's asking the system, so you need to find out what's the system first. The system includes
the car and the sand.
the car and the sand. So we need to find the momentum of the car and the momentum of the sand. Plus them together, that's the momentum of the system. Alright? So what's the momentum of the car?
Clear by
2,500 times 3, right? What about the sand?
it's not removing.
What's the initial momentum of the sand?
Zero.
What's the initial momentum of the sand? Why?
Because there's no velocity.
There's no velocity. The sand is here stored, right? So the initial momentum is purely just the car's momentum. Sand has no momentum because at this time the sand is not moving. It's stored. It's being stored here. There's no initial velocity for it. See? Then total momentum is just 7,500 kilogram meter per second. But what about the final speed of the system? What does the system means here? So previously the car is traveling at 3 meters per second. After the sand has been dumped into it, do you still think the car is able to travel at 3 meters per second? Will it travel faster or slower? Slower, okay. Then you need to find the final speed of the system, which is the car loaded with the sand. What would be its new velocity? What will be its new speed? 2 minutes, discuss with each other. 看这个情况，我们可能上不完 A2啊，所以这个下周四的考试，如果 A2没有上完，那没有上的部分就不会考，好吗？
我们就刚才说
I think I figured
Sam told me.
Lauren said you're wrong. You're wrong. Because Shana said so. Shut the hell up. Shana said I'm not I never
You were told. Please.
I'm not. I'm
Okay.
I'm salty.
Yeah.
Yeah.
I'm not how I'm saying. You don't care. You don't know what I'm talking about. It's just.
为什么杀的
Such a what was that?
More like retarded.
啊，这道题。
I think he's I don't think he's I think he's autistic. There's a difference between not autistic.
沙子放到这个车之后，这个车的新的速度。
I hope he's non-existent.
它原来是空车3米，
是的
现在沙子放进去，它还有3米，那它的新速度是多少？ How can we solve it? Luke.
So you find total momentum, which is then 500 divided by the after it's added to the sand, which is 4,000 kilograms, which is 1.9.
What's the key law that you should apply here in order to solve this problem?
Conservation.
Conservation of momentum. So we have already find the total momentum of the system before, right? Before it has 7,500 kilogram meter per second. That's the total momentum before, total momentum of the system before the sand drops into it. After the sand drops into it, there are a system. Internal force can be cancelled out. Is there any external force acting on the sand and the car? The external net force, such as the weight of them, is being balanced by the supporting force of the ground. So net external force is 0. Alright? If that's the case, momentum is conserved. So total momentum before is 7,500 before. That should be the total momentum after as well. And total momentum after equal to total mass after times its final speed. Total mass after is 25 plus 15, which is 4,000. So you just need to use 7,500 divided by 4,000 kilogram mass, which is the total mass, to find out the final speed, which is 1.9 meter per second. Get it? Questions? So far so good? Okay. Move on. Average force. Well, what's the changing momentum for the car? We just 0. Okay, this question, a lot of you guys will get it wrong here. Why? Because you don't separate the idea of the car and the system. We say that momentum is conserved for the system. Total momentum of the car and the sand as a system before is equal to total momentum of the sand and the car after. But is momentum conserved for the car? If you take the car itself individually, when the sand is an external thing to the car, it's not part of the car, right? So when sand drops to the car, will sand exert an external force on the car? So there's an external force for the car. So is momentum going to be conserved for the car? No, because there's an external force. Then how can we find out the change in momentum of the car? Well, how do we calculate momentum? Mass times speed. Well, you know the initial momentum. And now you just calculate the final speed. Can you calculate the final momentum of the car? Final speed of the car times mass of the car to get the final momentum of the car. Calculate it and see if it's the same as the initial momentum of the car. New velocity is 1.9.哎呀，我不会没有重新开我的录像吧？那完了。哦，我开了 ，nice。 你为什么乘以4？但是他现在问的是谁？对呀、你得用谁的是吧？对。One of the difficulties in DP is you need to identify the the object correctly, because you're gonna have multiple stuff, right? In MIP, it's easy because you only always have one thing. You just need to focus that, right? But here, should you use the mass of the car? Should you use the mass of the sand? Should you use the mass of the total? That depends on you. And you need to identify it because it's asking in the question. So you need to concentrate on the object that this question is asking for. Sometimes if you just assume, oh, it's asking for the system, doom, wrong. Oh. Okay, let's quickly give you the answer and see. Changing momentum is
Average force. Average force.
Okay, 我来做。So before, total momentum before is 75. Momentum after the car should be the mass of the car times the velocity of the car, which is 2500 times 1.9. That gives you how much? 4,750. So changing momentum is this much minus this much. Delta P equal to how much? 2,750. And then force is equal to changing momentum over changing time. So changing momentum divided by changing time, 4.5. So force should equal to 611 Newton. That's the correct answer. Got it? Okay. 好 ，homework，必须要做题啊，不做题你永远都懂不了。So homework would be question 19. So 3道题 question 19, 20, 21. 19, 20, 21.
Can you give us the 8.1 worksheet?